Up until now, all of the work that you've done plotting points and graphing equations has probably been with the rectangular coordinate system. But there's other coordinate systems out there, and one specifically that we like to do after some major work with the rectangular coordinate system is to look at what's called the polar coordinate system. Now, there's a lot of equations that cause us a little bit more of cumbersome work in the rectangular coordinate system that lend themselves to much easier equations to work with in the polar coordinate system. And so later on in future math classes, Calc 2, Calc 3, a lot of times we'll look at if there's an equation that is really hard to work with in the rectangular coordinate system, and it has a lot of x squareds and y squareds in it and different things that we can transform. We like to switch that over to the polar coordinate system and then be able to carry out the operations in that system. To get to at least a foundation with our polar coordinate system, this video is going to show you how to look at the vocabulary of the polar coordinate system, look at plotting points in the polar coordinate system, and also graphing equations that are in polar form, and then at the end transition points that are rectangular coordinates to polar coordinates, and equations that are in rectangular coordinates to polar coordinates. So let's get started. So here we're looking at the polar coordinate system, just giving some basic definitions. So when I talk about a point in the polar coordinate system, I still am going to have an ordered pair, but the ordered pair this time is r comma theta. Now r is kind of your distance you're going to walk away from what's called the pole, and theta is your rotation. One thing about the way that these points are given, they're given to me always in r comma theta, but a lot of times when we plot them, we're actually going to look at the idea of the theta first and then carry out the r. So that's one thing that you want to make sure that you're aware of when you're plotting points. Now the next thing that's also true in the polar coordinate system is that there are infinitely many different polar coordinates for the same point in a polar coordinate system. That wasn't true in the rectangular coordinate system. In the rectangular coordinate system, every point had a name, and that name was specific to that point. So there was a one-to-one correspondence between the point in the plane and the coordinates that defined it. In the polar coordinate system, we'll see that you can name a specific point in the polar coordinate system many different ways. Now, when we look at the examples of it, some definitions also is that for the polar coordinate system, we have a ray that's kind of pointing in the same direction our positive x-axis pointed in. This point that the ray starts at is called the pole, and that's similar to what we had as like the origin in our rectangular coordinate system. Now the coordinates of the pole are 0, comma, any angle that you list. So that's our coordinates of our pole. And then this ray is called the polar axis. Now I've superimposed circles that are concentric with the pole being their center, so we can look at plotting a few points. And not only will you have these concentric circles, you'll also have marks at specific angle measures as you go, so that the plotting is a little bit easier to do on a polar graph coordinate system grid. So the first one we want to graph is the point 2, comma, 90 degrees. So remember, we have our r first and then our theta. So when I'm starting to think about this, I want to think about standing at the pole and facing the polar axis. Now, angles off the polar axis that go up and around will have positive degree to them, or positive radian measure to them. And then angles that, when you're facing the polar axis, that you go down and around will be your negative, either degrees or radians. And then once you do the rotation, then you walk in that direction you're facing if your r is positive, and you actually walk backwards off of that if, for example, here my r is negative. So for 2, 90 degrees, I'm going to think about standing at the pole and facing the polar axis. Now from that, I'm going to rotate 90 degrees. So 90 degrees would be looking in this direction. And I'll go ahead and put that in so we see that we have our 90 degrees. And then I'm supposed to walk facing that way a positive 2 steps. So it'd be 1, 2. So there is our point on the plane that is 2, 90 degrees. That's our point on our polar coordinate system for that naming. Now let's look at the next one. It's 2, negative 3 pi over 2. So I'm looking at facing the polar axis. I'm going to go down and around 3 pi over 2. So here's negative pi over 2, negative pi, negative 3 pi over 2, and then I'm supposed to walk 2 steps in the direction I'm facing. So I actually get the exact same plotted points for this 2, negative 3 pi over 2. And I wanted to do that as an example so that you could see when they're telling you that infinitely many ordered pair descriptions exist for each point in the polar coordinate system, we've just found 2 different ordered pair descriptions for that specific point. Now how about part C? It's the r value of negative 3 and the theta value of pi over 4. So when I think of that being 90 degrees, my pi over 4 is that angle. And it's a positive pi over 4. So facing the polar axis, I'm going to go up pi over 4, but I'm going to walk backwards 3 steps. 1, 2, 3, because my r was negative. So this is the point for negative 3, pi over 4. So I just kind of imagine standing on the pole and facing the polar axis and going up and around the direction and then either walking forward for if my radius is positive or off of the pole walking backwards if my radius is negative when I'm going through and graphing these. So since we've done a lot of work with our special angles and some other like placements on there, a lot of times you will see where they will have, when you look at the polar graphs, like these angles marked just as guidelines to be able to then graph your points on the polar axis. Okay, now next up, there's some graphs that we want to actually get down in our notes so that we have an identification if they show up in a problem that we're asked to graph. We can say, hey, I know what that is, and with those characteristics of that type of a graph, be able to graph it a little bit quicker than just making a table of our r then thetas as we go. So the graph of theta equal alpha. So in a work with an equation, if they gave me theta is equal to, let's say, pi over 4. So in the equation, I just have like theta equals pi over 4. Well, then I would always have a pi over 4 here, and my radius would be anything. So I'd always have that angle that I would walk, but I would walk it either positive or negative. And so what I get from that is just a line that's through the pole. In your equation is just theta equals a number, and there's nothing in there about an action on it or a value for r or anything like that. You're just going to get a line through the pole. Now there's other lines and formulas, equations that we can identify. One is the graph of r sine theta is equal to a number. So if I have an equation that is r sine theta is equal to a number, then that's a horizontal line. So that's going to go horizontally at a spot on your polar coordinate system, and it actually goes horizontally through the point a comma pi over 2. So that would be something that would be nice to have if I could recognize that right off the bat. If you have the equation r cosine theta is equal to a, then you have a vertical line, and that vertical line goes through the point a comma 0. So in the case of our horizontal and our vertical lines, their equations were actually easier to identify back in the rectangular coordinate system, because remember, our horizontal lines were just y equal a number, and our vertical lines were just x equal a number. Here it's r sine theta equals a number for a horizontal line, and our cosine theta is equal to a number for our vertical line. And in a little bit, when we get to those formulas that help us switch between the rectangular and the polar coordinate system and vice versa, you'll see why that's what they transition to. Now, other graphs. The graph of r equal a. So if there's no theta in there, but there's just r, and r is equal to a number, well, that's going to give you a circle that's centered at the origin, because you walk out a distance, but it doesn't say what the angle is, so the angle could be anything, meaning that you just get your r equal a just being your rotation of your circle. So now that we have some of that foundation down, let's look at some other examples of graphing in the polar coordinate system. So now let's look at 3 examples of graphing. The first one is r equal 3. So remember, if we have r equal a, then it's a circle centered at the pole with the radius of a. So we have our a is equal to 3, my center is at the pole, my radius is 3, 1, 2, 3, and it's just the circle we are drawing here. So that is our graph of our equation, r equal 3. So circles that are centered at the origin with a specific radius are very easy in our polar coordinate system as opposed to in our rectangular coordinate system. Now how about the next one? R is equal to 2 sine 3 theta. Well, for this one, we need to make some table values in order to be able to see what this picture is going to be. So for part B, we are going to make a table of values that are r comma theta when we're graphing them out. And when I'm plugging in some angles, I realize that as we're going through, I'll want to make sure that I have values that I can get some good determination of the picture. So let's plug in theta of like 0, then pi over 12, pi over 4, pi over 3, pi over 2, 2 pi over 3, and then 5 pi over 6, and pi. And then we'll also look at going the rest of the way around. So after pi, we're going to do our 7 pi over 6, then 5 pi over 4, 4 pi over 3, 3 pi over 2, then our 5 pi over 3, next our 7 pi over 4, then 11 pi over 6, and finally our 2 pi. So each of those values to kind of get a good indication of our graph. Now, as we get more comfortable with what these equations graph, We won't need to put as many angles in because we'll know what to anticipate and then have a better idea of some more abbreviated angle choices instead of like this full gamut of it. But when we're first starting to learn about something, especially about the pictures that they draw and that sort of thing for equations, it's good to get a lot of points, and then even if we have it as overkill, we'll have that idea to then have as our foundation and carry on from there. Now, we're just going to take each of these angles and run it through this equation to get the r out. So if theta is equal to 0, you take 3 times 0 is 0. The sine of 0 is 0, and 2 times 0 is still 0. When theta is pi over 12, 3 times pi over 12 has a common factor of 3 that we'll remove, so that'll be pi over 4. The sine of pi over 4 is the square root of 2 over 2, and when I multiply the square root of 2 over 2 times 2, I get the square root of 2. For pi over 6, 3 times pi over 6 is 3 pi over 6, which simplifies to pi over 2. Now the sine of pi over 2 is 1, and 2 times 1 is 2. For pi over 4, 3 times pi over 4 is 3 pi over 4. The sine of 3 pi over 4 is the square root of 2 over 2. When I multiply the square root of 2 over 2 times 2, I get the square root of 2. So I'm just going to go ahead and fill out the rest of this table, and then we will plot them. Okay, so I filled out the table, and we're ready to plot points. Now, when we're looking at it, remember, you want to face the pole, you want to do the rotation, and then walk out on it. So our first point is 0, 0. So I have a 0 rotation and 0 radius. So that's a point at the pole. Now we're going to face the pole, turn pi over 12. So that's just halfway between 0 and pi over 6 is pi over 12. And then we're going to walk square root of 2. Now square root of 2 in decimal form is about 1.414. So I'm going to walk 1 and just a little shy of a half. Like just a little shy of 1 1/2. Now at pi over 6, so when I face pi over 6, I'm going to walk forward 2 steps. 1, 2. So that's going to be our point right there. Now, when I face pi over 4, so rotate pi over 4, walk forward about 1.4, and then at pi over 3, I face pi over 3, but I don't walk forward, so I'm back down on the pole. So this first part, when you go and you attach these, it's as you're going through the span of angles, because our table just has representative ones, but you're doing a smooth transition through these. So it's kind of like if you've ever played with a spirograph. That's what graphing in a polar coordinate system kind of makes me think about, is following that curvature as you're going through. So as I would follow this curvature, my pencil would have to go through these points. So you get kind of like a little loop there. Now let's look at our next angle. At pi over 2, I'm supposed to walk backwards 2 steps. So I would have this point. And then at 2 pi over 3, I'm back to 0 again. So actually we skipped some angle values in there that we had gotten with our earlier stuff. But we know it's going to do like this loop thing. So we are looping here, and then it goes like that. Now at 3 pi over 4, I'm going to go a square root of 2, which is 1.4, so about there. And then at 5 pi over 6, I'm at 1, 2. And then at pi, so I'm facing the polar axis, I turn pi, but then I don't step forward or backwards, I'm back at the pole. So I am making that loop. Now when I face 7 pi over 6, I go back 2. So I actually am tracing part of what I already did. And when I face 5 pi over 4, I go back a square root of 2. So it's at that point. So that whole thing where we have infinitely many different descriptions for the same point on the polar coordinate system, this particular graph finished by the time we got here, and so these other points are actually just retracing the stuff that we had before. So as you would go through and get the rest of it, it would just retrace this graph, getting through that. So that's the graph of r equal to sine 3 theta, and they call each of these little loops a petal. And so these types of equations are actually called roses. And when I have a rose where the coefficient in front of my angle is odd, I have as many petals as that coefficient is. So this is a coefficient of 3 in front of the angle in the form that gives me a rose. So I got 3 petals. If it were even, I would get twice as many petals as whatever that number is. So let's say I had 2 sine 4 theta, then I would have 8 petals. And this is because we wouldn't get that retracing part, so every time we went through the whole value, it would actually give me a new petal instead of retracing over one that we already had. So in general, if I have r equal a sine n theta, or r equal a cosine n theta, those are ones that will be a rose. And if n is odd, I have n petals. And if n is even, I have 2n petals. So it's kind of nice to think that, well, if n is even, I think of 2 being a divisor of an even number, and that's the one I have to remember to multiply the n times 2 for how many petals I get, just as a quick memory device. Okay, next up we're going to graph r equal 1 minus cosine theta. For r equal 1 minus cosine theta, we are going to again make a table of values so that we can have a whole bunch of points that we plot to get the picture. And then see if there's some key points that we could do that would help us, again, get these graphs a little bit quicker. So just to reiterate, with these examples, I'm plugging in a lot more angles than really will be necessary ultimately when you know more about the graphs. But when you're learning about something, it's good to be a little bit more encompassing with all of the values you get so you can really see the picture of the graph. So here we have, we're going to do our r theta. And we are going to plug in, let's go 0, then pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and then pi. And then we'll continue on with the 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, and then 11 pi over 6. So now when we look at this, we're going to take the cosine of the angle. Once we get that number, we're going to subtract that number off of 1. So when theta is 0, the cosine of 0 is 1. So 1 minus 1 is 0. At pi over 6, the cosine of pi over 6 is the square root of 3 over 2. And if I were giving this as like an answer to something, I would stay exact, but I want to graph this, so it's good to get the decimal approximation. So we're going to think about it again. The cosine of pi over 6 is the square root of 3 over 2. So that's about 0.8660. So when I take 1 and subtract 0.8660, I have 0.14 3, 4. Then for pi over 4. The cosine of pi over 4 is the square root of 2 over 2. Well, the square root of 2 over 2 is about 0.707. So when I take 1 and subtract 0.707, it's 0.293. Pi over 3. Well, the cosine of pi over 3 is a half, and 1 minus a half is a half. So that's equal to 0.5. Then at pi over 2, the cosine of pi over 2 is 0. 1 subtract 0 is 1. At 2 pi over 3, the cosine of 2 pi over 3 is negative a half. So 1 minus negative a half is 1 plus a half, so that's 1.5. Then at 3 pi over 4, our cosine of 3 pi over 4 is negative the square root of 2 over 2. So it's 1 minus negative 0.707, which is 1.707. 5 pi over 6, the cosine of 5 pi over 6 is negative the square root of 3 over 2. So that's a negative 0.8660 that I'm going to go 1 subtract negative 0.8660. So that's a plus. So that's 1.8660. And then pi. The cosine of pi is negative 1. 1 subtract negative 1 is 2. So I'm going to go again and just fill out the rest now that we have. So now that we have our table of values, we're going to graph some points. So here, your angle is 0, your radius 0, the point's at the pole. Your angle is pi over 6, and you're walking forward just 0.134. So just a tiny bit is what we're walking there. Now at pi over 4, we're walking forward 0.293. And then at pi over 3, we're walking forward a half. And then at pi over 2, so rotate pi over 2, walk forward 1. And 2 pi over 3, walk forward 1 and a half. Whoops, 1 and a half. At 3 pi over 4, walk forward 1.7-ish. At 5 pi over 6, walk forward 1.8-ish. And then at pi, walk forward 2. So far, as you think about that spirograph sort of thing, we're getting that. Now, for 7 pi over 6, we're 1.8660. And then at 5 pi over 4, it's 1.7-ish. So that's there, this is here. At 4 pi over 3, we have 1 and a half. So I need to move these out just a little bit. 1 and a half. At 3 pi over 2, so rotate 3 pi over 2 and walk forward 1. And then as we go through and we complete these dots, we get our graph that looks like this. And with this, you see how it kind of makes like a heart. So this is actually something called a cardioid. So if I have r is equal to a plus b cosine theta, or r is equal to a plus b sine theta, where the absolute value of a over b is equal to 1, then I get this thing called a cardioid. It's actually a subgroup of classification of polar equations that make what's called a lemniscate. But this one specifically for the cardioids, with the cosine, it's going this way. With the sine, it would go either that way. Now, if I identify that I have a cardioid, I really just need a few key points instead of doing all of these. I would want to have the point that it kind of comes into and then what its maximum point would also be. So I could definitely cut this back to a lot fewer angles than what we had in the example that we worked out. Okay, now that you have some of these graphs kind of under your belt and how to get other graphs, we're going to go on to see what the connection between the rectangular coordinate system and the polar coordinate system is, so we can transform equations and points back and forth between the two systems. So if we're going from the polar coordinate system to the rectangular coordinate system, we just find our x-coordinate by our cosine theta, and we find our y-coordinate from our sine theta. And this kind of goes back to those equations of lines that we already talked about, because our cosine theta is x, and x equal a number is a vertical line. And our sine theta is y, and y equal a number is a horizontal line. So that's why those curves translated into those graphs. But basically we just do that if we're going from our polar coordinate system to our rectangular coordinate system. Now what about from our rectangular coordinate system to our polar? That's a little bit more involved in terms of thinking that you have to do. So when we go from rectangular to polar, we have the connection from the Pythagorean theorem that r squared is equal to x squared plus y squared. And we also have that tangent of theta prime, tangent of our reference angle, is the absolute value of y over x. But we have to take that reference angle so that we get in the right quadrant for the dot that we're trying to find the coordinates in polar form for. And also we want to pick whether our r is positive or negative along with the angle that we're going to use, whether it be positive or negative, to get in the quadrant, again, where the dot is. So since there's infinitely many different ways to name, give a description of a point on the polar coordinate system, there are multiple different right answers you can get for going from rectangular to polar. Let's look at an example. So here I have a polar coordinate ordered pair, and I want to go to rectangular. So I just have that x is equal to r is negative 6, cosine of theta is pi over 3, and y is equal to negative 6 times the sine of pi over 3. The cosine of pi over 3 is a half, and negative 6 times a half is negative 3. And the sine of pi over 3 is the square root of 3 over 2. And negative 6 times the square root of 3 over 2 is negative 3 times the square root of 3. So that is our ordered pair for that particular polar coordinate. Next, let's take this rectangular coordinate pair and change it to polar. Well, first we have that r squared is x squared plus y squared. So r squared is our negative 4 square root of 3 squared plus 4 squared. So that gives me r squared is equal to, well, negative 4 squared is 16 times 3 is 48, plus 4 squared is plus 16. So I get r squared is equal to 64. So then our r is either plus or minus 8, depending on what angle we use with it. And then our tangent of theta prime, the reference angle, is the absolute value of 4 over negative 4 square roots of 3. Well, that becomes the square root of 3 over 3 when you rationalize it. So when I think of what angle gives me a tangent ratio of the square root of 3 over 3, so that theta prime reference angle is pi over 6. Now I need to think, where is negative 4 times the square root of 3 comma 4 on my rectangular plane? Well, that's left and up. So basically I just want to know what quadrant it is in. So left and up, that's in the second quadrant. So if I take my pi over 6 reference angle into the second quadrant going up and around, that would be an angle of 5 pi over 6. And so if I use the 5 pi over 6, then I want to walk out positive 8. So 5 pi over 6 and walk out positive 8 to get to that point. If we did negative, say, pi over 6, we would have had to walk the negative 8 to get to that dot. So that's just another way that you can name it. So that gives you some examples of changing your coordinates between the two systems. Next up, we're going to change equations. Let's look at changing some equations between the polar coordinate system and the rectangular coordinate system and vice versa. So here we want to write in polar form x squared plus y squared equals 32, and then x squared plus y squared minus 3y equal 5. Well, remember for each of these we have that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. So I have those that I want to keep in mind whenever I'm doing these transformations. Now the first one is x squared plus y squared is equal to 32. Well, x squared plus y squared is equal to r squared. So I just have r squared is equal to 32. And then when you take the square root of both sides, we get r is equal to the square root of 32. And I can simplify that to r is equal to 4 times the square root of 2. Now, normally we do like they're plus or minus, but remember that this is just going to give us a circle centered at the pole with the radius of the square root of 32, or 4 times the square root of 2. And so if I'm just doing that circle, whether I'm going facing the direction that many steps or backwards, I'll still be on that same circle. And in our equation, in our rectangular coordinate form, we have our x squared plus y squared equals 32. That's a circle centered at the origin with the radius of the square root of the number on this other side. So square root of 32, which is 4 square roots of 2. How about the next one? Well, again, I have this x squared plus y squared. That's r squared minus 3y is r sine theta is equal to 5. So I just have my polar equation is r squared minus 3r sine theta is equal to 5. Back, writing from polar back into rectangular. Well, when I look at this one, I view it and look to see if I have any direct substitutions for r cosine theta or r sine theta or the x squared plus y squared equals r squared sort of thing. And I have r cosine theta right there. So our cosine theta gets replaced with x. So I have 5x is equal to 35, which I could go ahead and divide both sides by 5 and get that x is equal to 7. So again, I see that this gives me a vertical line, really identifiable in my rectangular coordinate system, and just a little bit harder to see because we're not as familiar with it yet, but we'll get used to seeing that this still is that vertical line. And then part B, r equals 6 sine theta. Well, here I'm going to multiply both sides by r. So I get r squared is equal to 6r sine theta. Because at this stage it didn't have any of these replacements. But when I multiply both sides by r, I have r squared, which is x squared plus y squared, is equal to 6 times r sine theta is y. So I actually get, and I'm going to bring that over here to do a little bit more work on it, I have my rectangular equation there, but x squared plus y squared equals 6y. I can subtract the 6y over. I have x squared plus y squared minus 6y is equal to 0. I can complete the square on the y's. So 1/2 of -6 is -3. -3 quantity squared is 9. So we'll add a 9 to both sides. Factor your perfect square trinomial, and we get x squared plus our y minus 3 quantity squared is equal to 9. So I see that the equation that I get in rectangular form is a circle, and it's centered at 0, 3 with a radius of 3. So I can see that in my rectangular coordinate system because we've worked with that more, but the more we work with our polar coordinate equations, you would start to identify them here as well. Well, that's it for our work and examples of working with the new coordinate system, the polar coordinate system.